everyone, welcome to GDC Classes English. So I hope you all are done with your weekly test this week. So the syllabus for the same was from our pharmaceutics, whereby we have seen about the rheology and dispersion system. So the test was assigned on the basis of the topics which have been covered in your regular classes, as well as you have it on YouTube as well. So let's see the explanation of the questions. I hope it was a great one for you all. Please comment down how much have you scored. If any doubts you had, you can please comment down below. I will check them all. Otherwise, you can look for the explanation which I am going to discuss today. Okay. So let's jump into the first question of the day. So the first question of the day is a reason assertion, a simple one, and the question says kinematic viscosity is obtained by dividing the absolute viscosity of a liquid by density, right? So exactly this is the formula whereby you have viscosity upon density. Yes, this is the kinematic viscosity. This is correct. The unit of kinematic viscosities are Stokes and centistoke. Yes, this is also correct. So both the statements are actually correct. Okay. So the correct answer must be option number A. Okay. I hope this was a very simple one. Based on the formula itself, we have density, viscosity upon density, and the units being the Stokes and the centistoke. Next question, here you have to match the columns with the option number 1 is the viscosity of the gas, then viscosity of the liquid, then fluidity of the liquid and activation energy. Now here the explanation must go on with the right column number 2. So viscosity of a gas. It is very clear that we are using two different states, right? One is gaseous, one is liquid. So based on their particle behavior, nature of the particle, their viscosity may vary with the temperature. For example, for the gases, if you increase the temperature, the viscosity usually increases. But not the case for the liquids, whereby if you increase the temperature, usually the viscosity decreases. Here the difference is mainly due to the difference in their interparticular forces, right? Intermolecular forces and the nature and the kind of particle as well. So here you have a viscosity of gas which exactly increases with the increase in the temperature. So for P we have 2. So we have correct option 1 or C because P second. Okay. Then we have viscosity of liquid. Now that is going to reduce with increasing in the temperature. Third, fluidity. Now fluidity is nothing but the reciprocal of viscosity, right? From the name itself it is clear. So R3 and in this R is 4. So we have correct answer as option number A. So there is always an answer which is the tiebreaker. So from the name itself it is clear, fluidity, that means fluid, that means contents are in the flow, right? Then viscosity, it might indicate the material are slight viscous. So viscosity and fluidity are almost inversely proportional. So option number A is going to be correct. Okay. Next. Again match the column. So number 1 is the plastic flow. Can you see these are all mostly the types of the non-Newtonian system. We have plastic flow, pseudoplastic and dilatant ones. Plastic systems are called as Bingham bodies. Plastic systems are called as Bingham bodies. One more additional important point was that in the plastic system we usually require a particular initial yield value, a force up till yield value which is required. Only after that the material is going to show the actual rheological characteristics, right? So they are called as Bingham bodies. Second we have is the pseudoplastic ones. So pseudoplastic ones are known as shear thinning system because their ability to flow very easily. Third we have dilatant systems which are known to expand, so they are called as shear thickening system. And yes, we got the apparent viscosity as well. So I hope it is clear. Plastic we have Bingham body. So correct answer will be none other than option number first. So even if you knew at least one of it, the question would be simple. However, other are very important based on the previous patterns. So plastic flow, here it must be clear that here an additional yield value is required. For the pseudoplastic, here the graph starts from the origin, no yield value extra is required. In this case mainly gums, Traeger guns, they usually show this type of behavior, right? In the plastic systems you may see we have a equation for the plastic viscosity in which we have our main shear stress minus the yield value. Yield value will be the additional force that is required so that the material is able to flow. Then G will be the rate of the shear. So this relationship is valid for none other than our plastic system, which are Bingham bodies. Shear thinning are pseudoplastic, and shear thickening are dilated systems. Okay. I hope that is clear. Next. So this equation represents which type of flow? So the question was again on that equation. You can see only in the equation where additional yield value is subtracted here. So this is for our plastic system where we have an additional force equivalent to the yield value. So it must be the plastic system. Just before this I have already explained it. Okay. Next question. This is the same explanation. Next, the most apparent characteristics of a thixotropic system. So thixotropic system in the Newtonian system, and we have a non-Newtonian system. In the non-Newtonian system, we have time dependent system, and other we have time independent system. In the time dependent systems, there are generally breakdown of the structure, and it is again coming back to the original state. For example, in the thixotropy, we have gel, sol, gel conversion. Initial state was gel, then when you apply the shear stress, it will become sol. Then it will be again, if you leave it for a good period of time, there will be the isothermal and reversible conversion back to the gel state. So we have gel, sol and gel conversion in the thixotropic system. So here it is quite evident that the yield value of the system, no, it is in the time independent system, the plastic system, there the yield value is required. The constant viscosity changing with the changing rate, shear rate. No, it is not possible because gel, then sol, gel, every step we see the change in the viscosity. In fact, if you have to plot the rheogram, it should be like somewhat like this. Originally gel state, then sol state, then again back to the gel state. Linear relationship between shear stress and shear rate. No, the relationship is not linear because again they are coming back to their original state. Hysteresis loop in the rheogram. Yes, there is a hysteresis loop in the rheogram. Okay. So our correct answer must be option number A. Right? Next, the house of card-like arrangement of the crystalline plate producing flow curve is a rheological feature of. Can you exactly know of what is house of card appearance? We have discussed, I have put this name where I have told you about the hysteresis loop, I have told you about the bulge and spur. In the bulge I have told you they have a characteristic up curve, right? In the bulge I have told you there is a characteristic up curve somewhat like this, right? In this spur it is somewhat like this. So in this bulge we say there is a house of card like appearance. And the example of the bulge is going to be the bentonite gel. It is going to be the bentonite gel, right? For the spur, it is going to be the procaine penicillin gel. So this is for the spur, but house of card will be option number B, bentonite gel. Okay, for the bulges, option number B. Okay, characteristic you can see here bulge, and here we have spur. Okay. Next, cone and plate rheometer is mainly used for. Now, Newtonian, non-Newtonian fluids, based on the viscometers, we usually take the single point viscometer and multi-point viscometer. For the single point viscometer, it is for the Newtonian system. For the multi-point, it is for the non-Newtonian and Newtonian both. Single point, we have 𝙂. I have already told you this trick. 𝙂, falling sphere, Oswald capillary, Hoppler, right? Hoppler is a type of falling sphere, Oswald is a type of the capillary viscometer. Similar, we have multi-point, we have CCB, cup and bob, cone and plate, and Brookfield viscometer. So for the non-Newtonian one, we have our cone and plate viscometer for the non-Newtonian systems. I hope this is right for you all. In the multi-point viscometer, single point, we have one multi-point. Single point is specifically for Newtonian fluids, multi-point is for the non-Newtonian fluids. Okay. Next, which viscometer measures viscosity based on the time of liquid to flow through the capillary end and is most suitable for the colloids and emulsion? Capillary, can you imagine capillary, where I have told you capillary rise phenomena you have seen, right? In the surface tension you have seen like that. Here the phenomena that is used is capillary. So 𝙂 I have just told you single point. 𝙂, falling sphere, Oswald capillary, Hoppler. Hoppler is a type of falling sphere. Oswald is a type of capillary viscometer. So we have Oswald viscometer because here you already talk about the capillary, right? So option B must be truly correct. Okay. Okay. Next, arrange the following in ascending order of their absolute viscosity at 20 degrees Celsius. Water, olive oil, glycerin and chloroform. Right. So, the highest absolute viscosity is going to be for the glycerin. Right. Then it must be for the olive oil. Right. Then it must be for the olive oil. Glycerin, then it is for the olive oil, then it's for the water and then for the chloroform. So option A must be directly correct, right? For the chloroform it is around 0.5, for the water it is around 1, for the olive oil around 100 and for the glycerin is around 400. So can you see with the values? It is clear that option A will be correct. Okay. So here for castor oil 1000, for glycerin 400, for olive oil 100, ethyl alcohol 1.19, water we have 1, chloroform we have 0.563. Okay, next question. Which of the following statements about the non-Newtonian system is correct? Non-Newtonian system, time dependent, time independent. Time dependent we have thixotropic, we have rheopectic system. In the time independent systems we have are plastic, pseudoplastic and dilatant system. So first option, non-Newtonian system follow Newton laws. No, that is why they are, for a reason they are called as non-Newtonian. So option statement 1 is actually incorrect, right? Non-Newtonian follow Newton's law of fluid. So this is going to be incorrect. So we have first incorrect, third incorrect because option 1 is there. All of above will be incorrect. We already got our answer, but let's see the explanation as well. Most pharmaceutical fluids like emulsion, suspension, ointments are non-Newtonian. This is a correct statement. Non-Newtonian exhibit plastic, pseudoplastic, dilatant system. Just now we have already told you this is correct. Colloidal solutions always behave as Newtonian fluids. This is also correct. So even if you know the first answer, it would be very, very clear. Okay. So we have second and third as the correct. No, colloidal solution, they are saying they follow Newtonian. No, they follow non-Newtonian. They must be included in the dispersion system in the non-Newtonian. The fourth one was incorrect. So option 2 and 3 is correct. Okay. Next question. Thixotropic system contain asymmetric particles that pass through numerous points of contact. Set up a dash through a sample. Loose three-dimensional network, rigid solid structure, uniform solution or crystalline lattice. See, if we were to talk about the solution, we are not talking about solution. We are saying gel, sol, gel state. It is a convertible state. That is a thixotropic behavior. So if you had a rigid structure, how would it be possible to interconvert? There must be some loose structure, loose three-dimensional structure, after which again they are coming back to the original state. There is a rebuilding of structure that is happening. Only it is possible when we have a loose three-dimensional structure. Basic thinking if you have to apply, this would be very, very correct. Next, negative thixotropy. Now, first of all, it must be clear what is thixotropy, what is rheopexy, what is negative thixotropy, what is negative rheopexy. So, in all the class, I always tell you, in the thixotropy, we have gel to sol to gel conversion, right? So, negative thixotropy will be sol to gel to sol conversion, right? But rheopexy and negative rheopexy would be the same. There is a simple difference that you cannot let this breakdown be very slow, but it is fastened up using the additional force of vibration, any agitation or any stirring that is applied, that we have discussed in regular class. Okay, negative thixotropy. So option 1, a decrease in the resistance to flow within the time. Is the resistance decreasing from sol to gel? No, right? A constant resistant, there is no constant because the state is again and again changing. And increase in the thickness or resistance to flow with increase in the time of shear. Can you see, it was sol, now it turned up to gel state. So the thickness would definitely increase or the resistance to flow would definitely increase. So option C must be clearly correct. Okay, next question. According to the text, biological material that show viscoelastic property, that means they are viscous as well as elastic. They can be blood. Very important and very simple example to remember is blood, right? Urine, sweat, not at all. Saliva, bile, plasma, tears, no. Blood, sputum and cervical fluid, they are the example of which contain the both visco and elastic properties. Okay. Next, match the pharmaceutical areas with their rheological significance. Fluids, solids, quasi-solids and processing. Right. So, fluids, spreading and adherence on the skin. Flow of powders from hoppers into dye cavities. Mixing, pouring, pumping behavior. Production capacity and efficiency. So, number one, can you see fluids? So, you can mix the fluids, you can pour the fluids, you can see their behavior, right? Then we have quasi-solids. Quasi-solids show the spreading and adherence to the skin. Third would be the solids, right? Solids, here we have the flow of powder from the hoppers into the dye cavity, right? Then we have processing. So processing will be the production capacity or the relevant to the efficiency of the process. So the question was very broad, but it can be still answered with a simple logic. So option A is here correct. Okay. Next. The spur-like protrusion. We have seen bulge, we have seen spur. Spur-like protrusion on the up curve represents what? Spur-like protrusion. You have seen bulge, right? Spur is somewhat like this, right? So, spur-like protrusion represent what? We already know that hysteresis loop is forming. That means there is a continuous structural breakdown that is happening. Rebuilding of structure is also trying to happen. So, in that case, the rate of shear and the shear stress are playing a great role, right? So, continuous rebuilding of structure here is happening. Breakdown, rebuilding, there is a point in this hysteresis loop. You can spot that there will be a sharp point where the structural breakdown will happen at a low shear rate, right? So again and again here this in the hysteresis loop, be it bulge, be it spur, it is actually shown. Okay, so option B will be correct, right? So we have example of the bulge. We have bentonite gel structure, we have house of card like appearance, rheogram with a characteristic bulge in the up curve, somewhat like this, caused because of the swelling of the bentonite magma. Next we have spur, procaine, penicillin G, they form a better height and structures. Here we can see the protrusions here like in the rheogram, which represents the structural breakdown at a low shear rate. Okay, next, colloidal dispersion can be best characterized by which of the following features? So in this case we have particle size greater than 0.5 micrometer visible under the ordinary microscope. Here you can spot the problem. Visible under the ordinary microscope. Particle size can range from 1 nanometer to 0.5 micrometer, but they are not visible from the ordinary microscope, but they require an electronic microscope. On the basis of size and resolution, we can see it is not resolved with the ordinary microscope, but it requires the electronic microscope. Okay. So molecular dispersions, they have a size almost around or less than 1 nanometer, which is so small. So we generally call it as true solution. Then we have molecular dispersions in the range of 1 to 0.5. Above that we call them as quartz dispersions, in which the suspensions and emulsions are usually talked about. Okay. Next, which of the following correctly matches the type of the colloid with its typical examples? So here we have our lyophilic colloids and lyophobic colloids. Lyophilic colloids are quite easier to make, right? Lyophilic colloids are easier to make, but lyophobic colloids require special method of preparation. If you understand my words, now you will be able to find it the answer correctly. Lyophilic colloids are actually easy to make, but lyophobic colloids require a complete process for the preparation. The association colloids, mainly the surfactants, are classified in the association type. So in the lyophilic, they have given example of gold, silver. Lyophobic, they have given the example of rubber polystyrene. No, rubber polystyrene, they are included in the lyophilic, not in this. Also in the association, they have given sulfur in water. I have already told you in the association we generally use the surfactant. So only in this case we can see the surfactant was mentioned. Rubber polystyrene, this is correct, lyophilic. Gold and silver be the lyophobic. Okay. So correctly matched pair will be the option number B. Okay. So you can see lyophobic we have gold, silver, sulfur, arsenous sulfide, right? We have association, we have our surfactants. In the lyophilic we have rubber and polystyrene. Okay. Next. Which of the following statement is true regarding the lyophobic colloid? They are thermodynamically stable and easy to prepare. Lyophobic. This is true or not? I have just told you this statement would be highly incorrect because lyophilic colloids are easy to prepare. They are reversible in nature and highly solvated. No, lyophilic ones are highly solvated. Lyophobic ones, they have lesser affinity for the solvent. Third, they are largely inorganic, highly charged and require special method of preparation. Can you see? I have told you the similar line that lyophobic colloids do require a special method of preparation. So option C is correct. Direct statement based question was given. Okay. Also, please remember the lyophilic colloids have a high affinity for the solvent, so they have a greater solvation as compared to the lyophobic colloids. Also, lyophilic colloids are less charged; these are highly charged. Okay, and thermodynamically stable are the lyophilic ones. Lyophobic ones are thermodynamically unstable. Okay. Next, which of the following is not considered as a kinetic property? Brownian motion. Kinetic property represents some sort of movement, right? Then we have diffusion, then we have osmosis, and then we have Tyndall effect. So Tyndall effect is a scattering of light which is visualized. So it's an optical property. In all other the movement is happening. So that is all these are the kinetic properties, but this one is the optical property of the colloid. Okay. Next, which of the following regarding the Brownian motion is incorrect? Right. So we have, it can be observed with the particle as large as 5 micrometer. It is clear. Brownian motion, which is the zigzag motion of the particle, is visible till the 5 micrometer also. It is caused by bombardment from the molecules of dispersion medium. Yes, it is somewhat the movement of the particle within the dispersion medium. Velocity of the particle decreases with increasing the particle size. Velocity of the particle increases with decreasing the particle size. No, generally the viscosity of the particle does not decrease with increasing the particle size. Okay, option C is incorrect. So velocity of the particle increase with decreasing the particle size. Okay, just a second. Velocity of the particle increase with decreasing the particle size. Here it might be incorrect. Here this might be incorrect. Okay. Brownian motion, it's a zigzag motion. It is clear. The bombardment is clear. The motion of molecules cannot be observed because molecules are too small to see. Till this point is clear. The velocity of the particle increases with decreasing the particle size. This is quite obvious because the particle, once they are small in size, they are much more easy to move out, right? So here the option that must be incorrect would be velocity of the particle. Yes. So here this one, option D is correct. Velocity of the particle increases with decrease in the particle size. This is correct. This one would be reverse of it. Either the option was given wrongly, but first, second and fourth are correct. C option is a little bit mixed up. Okay. Okay. Next, match the following with the gold number. Gold number is very important. It is relevant to the protective ability of the colloid. For example, for the gelatin, everybody knows that gelatin has around 0.005 to 0.01. So first we have A option for the third. Only if you know this, you could have easily ticked that correct answer will be option number A. Then for the albumin we have around 2. Then for the acacia we have 0.1 to 0.2. For the sodium 𝚤𝙎ate, it is around 1 to 5. For the tragacanth, we have around 2, right? So even if you remember at least for gelatin and for tragacanth, you would be easily answerable. For gelatin, then for the albumin, acacia, tragacanth and sodium 𝚤𝙎ate. Next, Kraft point of the surfactant. Can you relate it? Kraft point with CMC we have discussed in the class. One was cloud point, one was Kraft point. So Kraft point would be the temperature. at which the solubility of the surfactant is equal to the critical micellar concentration. I hope with the definition you must have figured it out that what was the correct answer. So direct definition based question it is. So we need not to say that option B is correct. Okay. So it is quite relevant that correct answer would be option number B. Cloud point was the point where the cloudiness appears. Right. According to 𝘿𝙄𝙎𝘾𝙄𝑼 theory, which of the following is responsible for influences the particle-particle interaction for the 𝘂𝙂𝙎𝘾𝙄𝑖𝑑s, right? So here we have temperature of the medium. Because 𝘿𝙄𝙎𝘾 theory is based on the interparticular distance, here the temperature relevance is not counted. Distance between two dispersed particles, this is the basis of the 𝘿𝙄𝙎 theory. If you remember, the primary minimum, the secondary minimum, right? So here the repulsive and the attractive forces based on the interparticular distance, they are well counted. Okay, so we have our distance between two dispersed particles as the correct answer. Okay. Next, here you can already see the primary minimum, right? This stage, and we have a secondary minimum stage. Primary minimum is the region of the maximum attraction. Secondary minimum is going to the region of the coagulation. Okay. Next, in which of the following method ions or molecules enhanced by applying the potential difference across the membrane? So where the membrane has asked, it must be clear that they are talking about the dialysis, semi-permeable membrane through which the material passes. But they have applied the potential difference, so the answer relates to much more of the electrodialysis, right? So here the electrodialysis, these are all the methods of purification of the colloidal particle, whereby any impurities or any other ions you want to eliminate, you choose a dialysis membrane for a particular size and you disperse it. And if you generally the process is very slow. To fasten it, we usually apply the potential, right? So here the electrodialysis would be applied. Okay. Next, the instrument used to observe the particle responsible for the Tyndall cone here is microscope, ultramicroscope, spectrometer or centrifuge. So the basic microscope is generally not used, but the ultramicroscope here is used. Okay. Okay. Next, which of the following statement about the pharmaceutical suspension is correct? Pharmaceutical suspension are homogeneous system. Are the pharmaceutical suspension homogeneous? Not at all. They contain two phases, disperse and dispersion phase and medium. A good pharmaceutical suspension has a particle size ranging from 2 to 40 millimeter. Not at all. This is a quite big size. In quartz, quite smaller size. In quartz suspension, the solid particle size ranges from 10 to 1000 millimeter. Here the units they have asked is incorrect. There must be the micrometer, right? The solid phase in aqueous suspension is completely dissolved in the liquid medium. So correct answer must be option number 3rd. Okay. So correct. Next, regarding the measures to prevent the crystal growth, which statement is incorrect? Which statement is incorrect? So option A here says avoiding size reduction during the manufacturing helps crystal growth. Okay. Which of this statement is incorrect? They are asking, right? So increasing the viscosity reduces the crystal growth. This is also correct. Using a metastable form is preferred to prevent the crystal growth. Actually, the stable forms are usually employed to reduce the crystal growth. Here they are talking about the metastable form. Although metastable form is not unstable, but still we generally prefer for preventing the crystal growth that particle needs to be in a particular narrow range. We usually tend to use much more stable form, or we add a wetting agent or avoid any temperature fluctuations, or even increase the viscosity. So these are the methods by which we can prevent the crystal growth, but not by using a metastable form, right? So we can select the particle in a particular size range, selecting more stable crystalline form, avoiding the size reduction during the manufacturing, incorporation of the wetting agents, increasing the viscosity, or avoiding the temperature extremities. Okay. Next, which of the following statements about suspension is incorrect? So here we have penicillin G suspension is more stable than penicillin G solution, right? Next, corticosteroids are injected as suspension. the suspension form of a drug always have a lower bioavailability than a tablet form? Not at all. If you look at the bioavailability role, we have seen the solutions and then the suspension, they have the highest bioavailability, right? So this is a direct incorrect statement, option number C, right? Okay. So drugs in the suspension do exhibit the higher bioavailability, but from not higher as compared to the solution state, but definitely from the tablets. Next, according to the Stokes law, the rate of the sedimentation of the particle is directly proportional to what? So here you have seen in the Stokes law equation, we have our density difference, right? Then we have inversely proportional with the viscosity, but directly proportional with the density difference. Okay, so viscosity, it is inversely proportional, but density, they are actually in your dispersion medium. Then square of the particle diameter. This is also correct. If you remember the equation, it would be d square rho s minus rho naught into g upon 18 eta. So we directly have given two references, that it is directly proportional to the square of diameter and inversely proportional to the viscosity. Density of the dispersion medium. Here if they have mentioned about the difference in the density, that can be considered, but here only for the dispersion medium they have said. So correct answer must be option number C. Okay, square of the diameter. Yes. Next question. Which of the following is a characteristics of ideal pharmaceutical suspension? Number 1, sediment should form a hard cake at the bottom of the container. Okay. Next, solid particles should be settled rapidly. Third, the suspension should be easily redispersed on moderate shaking. Fourth, oral suspensions do not require any consideration of the taste. So for a suspension, ideal suspension, it is obvious that they are a biphasic, containing a biphasic system where we have a dispersed phase and a dispersion medium. So generally the maintaining their ability so that they do not form a hard cake, that is very, very important. But here it is mentioned that the suspension should be easily redispersed on moderate shaking. This is most important because we have two different phases that we are making in a suspension, so they must be redispersible. We have seen in these suspension labels, they say that it should be shake well before use, right? So if the hard cake formation is there, even if you redisperse, that is not going to form into a ideal suspension. So here option C is going to be the correct one. Okay. Next, which of the following statement about the flocculated suspension is correct? So we have two types, we have flocculated, we have deflocculated ones. Both can differentiate based on how the particle settling is there. So particles settle independently and form a hard cake. When we are talking about the flocculated one, there should not be any consideration of the hard cake formation. Sediment is loosely packed and can be redispersed. Then particles experience strong repulsive forces leading to slow sedimentation. Then supernatant remains cloudy due to uniform particle dispersion. So in the flocculation, one thing is clear to us, that sediment is usually closely, very loosely packed and it is easily redispersed, because if the particles are sedimenting, but the particles are sedimenting like they form a stronger bond, they form a hard cake, then they will not be easily to redisperse, which is a kind of we see in the deflocculated ones. But in the flocculated ones, they are loosely packed and easy to redisperse, right? So you can see we have deflocculated suspension, which is much more pleasant in appearance, where the particle do exist as separate entities. Rate of sedimentation is slow. Particles do settle here and they are closely packed, so they form a hard cake in the deflocculated one. The hard cake formation means their redispersibility is very poor, right? Then in the flocculated one, as the name suggests, floccules are actually the particles which have very less interaction between them, right? That means they may form loose flocks, right? So they can be redispersed. The hard cake formation is not generally seen. Sediment here, it forms loose packing and does not form a hard cake, right? Next, which of the following statement is correct regarding to deflocculated suspension? We have already seen this. particle exist as separate entities. We have seen this one, right? So particles do exist as separate entities. Sediment is closely packed and will form a hard cake. We have seen that in the deflocculated ones, the hard cake formation is done and it is not redispersible. Supernatant remains cloudy due to uniform dispersion. Yes, it is clear. Rate of sedimentation is slow because the particle size is small. This is also clear. So all the options are actually correct. Right here we can see the rate of sedimentation is slow because the particles are small in size. Right. Here we have our supernatant that remains cloudy. In the flocculated ones, the sedimentation is faster, so supernatant remains much clear. Next, choose a correct combination. An acceptable suspension should not exhibit settling of dispersion of solids. This is clear. If it has to be settling down, then it might not be an ideal suspension. But if it is redispersible, then we can say it must be fine. Then reducing the particle size ensures Brownian motion, which helps to maintain the suspension stability. Both the statements here, there are two different statements, both make logic. Yes, around 5 micrometer we have seen Brownian motion is shown, but if you reduce the particle size, then it is quite evident that the stability will be much more improved and it will not lead to the settling of the particle in the dispersion. So both the statements are actually correct. Okay, next. Which of the following statements about the Brownian motion in the suspension is false? Option 1. Brownian motion can prevent the sedimentation of the particles. Okay, then particle size, because Brownian motion keeps the particle engaged, they keep the particle moving, so the generally sedimentation does not take place. Particle size and viscosity are major factors that affect the Brownian motion. Obviously, if you continuously increase the particle size, there must be increase in the viscosity and that may lead to reducing the Brownian motion. No sedimentation diameter is the particle size below which sedimentation is negligible. Particles in most suspensions always exhibit Brownian motion due to smaller particle size, right? So in this case, particles in most suspension always exhibit motion due to smaller particle size. In the suspension, the particles are already not small, they are quartz dispersions, right? So most of the students may wonder about the option 3rd, but actually option D was correct, okay, because that was the false statement. So in the case of theory of Brownian motion, no sedimentation diameter is the size of the particle below which the Brownian motion will be sufficient. Only then the particle will easily disperse. Read the following statement about the correct flocculation structure vehicle and identify the correct statement. Number 1. Controlled flocculation combines the principle of flocculation and structure vehicle to obtain improved suspension. Okay. Next, the structured vehicle prevents aggregates from settling, improving the suspension ability. We have discussed about the structure vehicle where I have told you a flow chart how the formation take place if you add flocculating agent, deflocculating agent, along with you add a structure vehicle. If you remember, option P was also fine, option Q is also right. Then hydrocolloids, which are anionic, are always compatible with the cationic flocculating agents such as aluminium chloride. So here we have charges which are opposite. That means the attraction will be happen. That means aggregation is quite possible at this stage. Right. Next, unstringent mass indicates physical incompatibility. This is also clear. So R is only the incorrect one. Yes. So moving on to our next question. Which of the following is not a cause of the crystal growth in the suspensions? Right. Option A, addition of a suitable suspending agent. So if the suspending agent would be added, then there would be no crystal growth, right? So option 1 is directly correct. Oswald ripening is relevant to the crystal growth. Polymorphic transformations, then temperature changes. We have seen that addition of a suitable suspending agent would definitely avoid the particle growth. Okay. Next, statement 1. Physical stability of a suspension means that particles remain uniformly distributed throughout without the sedimentation. Yes, it is correct. Statement 2. In practice, a suspension is considered physically stable if the settled particles can be easily redispersed by gentle shaking. Both these statements are correct. We have seen how the particle size impacts the growth of the particle, settling of the particle, how the type of the dispersed phase and dispersion medium do impact, how the viscosity and temperature affects. So any ideal suspension would be the one that would be redispersed. So both these statements are actually correct, which explains the physical stability very clearly. Okay, next. Emulsions are thermodynamically stable system consisting of two miscible liquid phase. Can you spot the incorrect thing? Miscible. Two immiscible ones are usually used, right? So statement 1 is definitely false. Statement 2, emulsions are coarse dispersion having a globular size of around 0.1 to 100 micrometer, which is correct, right? So second statement is correct, but the first one is definitely incorrect. So option C would be our most definite answer. Also, they are thermodynamically unstable, which was mentioned as stable. Okay. Next, Oswald writing in suspensions refers to breakdown of large crystal into smaller ones. No, it is relevant to the growth of the particle. Growth of larger crystal at the expense of the smaller ones. This mentions the one that we have already been talking about. So it is nothing but the growth of the larger crystals, right? Okay. Next, 40. The use of emulsions in a pharmaceuticals is declining. Okay. Next, emulsions show stability problems and have a short shelf life. Both of these statements are actually correct. See, biphasic systems are not easy as we seem or read in our textbooks. Once you start formulating, you will see that this is actually causing a lot of problems. Maintaining the particle in a particular state for longer periods is extremely difficult. Particle growth happens, then the sedimentation happens, the precipitate start forming, or cracking, creaming, or final breaking of the emulsion take place. So it is very difficult across all the temperature ranges to maintain the shelf life of emulsion. So this is actually, both the statements are correct. Okay, this is its prime limitation. Next, an oil in water emulsion, which of the following is true? So oil in water type emulsion, you all know the oil will be the dispersed phase and water will be the dispersion medium. The dispersed phase is water. No, the dispersed phase, okay, dispersed phase will be oil, dispersion medium will be water, right? Both are continuous phase are oily. The dispersed phase is solid and continuous phase is liquid. It is oil in water, not anything else in water. So here option D, which is the dispersed phase, is oil and continuous phase is in the liquid, which is internal or external phase as well. Micro emulsion contain globules of approximate size. So micro emulsions are little bit on the larger side, right? So generally the nanometers, we have seen the size of the emulsions. From that little higher size, we can say from the point of emulsions, a little smaller size, it is micro, then it will be nano emulsions. We have emulsion, we have micro, and then we have nano emulsion. If we have macro, that would be larger emulsion, then micro emulsion, and then nano emulsion. So from a general spectra, we have a lesser size of around 0.01 micrometer, right? So option C would be correct. Okay. Next, match the column. Now here is the phase volume ratio with the type of the flow or the behavior of the fluids, right? So at 5% phase volume, at 50%, and at 74%, right? So at the 5% we have a pseudoplastic flow because they are easily able to flow as compared to the phase volume ratio. If you take, they are the material which have a lesser viscosity and easily flow. So 5% will be the pseudoplastic system, right? Then we have A. Then for the A, which will be, no, actually for the, there is a little bit mismatch here, phase volume ratio and the type of the flow. Okay, 5, then 50, then 74. 5 will be for the Newtonian system, whereby the rate of the shear and shearing stress both are directly proportional. That would be possible only at a lower percentage of the phase volume, right? Then for the 50%, that will be the pseudoplastic system. Then for the 74, it will be the plastic system. Now that leads to its consistency because of the phase volume ratio 5%. It would be offering the Newtonian. It would be little higher, but still on the medium side. It will be pseudoplastic, which are shear thinning system, and 74, which is the higher side, higher viscosity plastic systems. Right. The dye solubility test, amaranth and methylene blue. These are the example of. Now these both are used for your test. You have seen in the case of the emulsion test, oil in water type or water in oil type. These are mostly the water soluble dyes that may color up the even water is in the dispersed phase or in the dispersion medium, right? So we use this dye solubility test for the emulsions. Okay, next. Foams are what? Foams are coarse dispersion of liquid in gas, fine dispersion of solid in liquid, or coarse dispersion of gas in liquid, thermodynamically stable liquid in liquid. When we talk about foam, definitely one of the phases is going to be the gases. Most importantly, the dispersion medium is going to be in the gas or the dispersed phase. At least one of them has to be in the form of gas. Only then you take it as a foam, or we'd say aerosol. But in the foam, we usually use a liquid and a gas. The gas will be in the dispersed phase, while the liquid will be in the dispersion medium. So it will be a gas in liquid dispersion. Okay. Okay. Next, match the column bentonite acacia triethanolamine with the type of the colloid, right? So here we have our bentonite. So bentonite hydroxide aluminium silicate is a solid particle, right? For the acacia forms are acacia, and then we have our triethanolamine, right? So acacia forms the hydrophilic colloid, right? Then we have triethanolamine, which is nothing but a surface active agent. It must be clear that this is a surface active agent, right? So we have option number 1 as the correct answer. How did I judge that it is a surfactant? If you remember, cationic, anionic, non-ionic and zwitterionic, we have 8 here, only 8. So this is nothing but a anionic type of surfactant. So this is mentioned here that it is an anionic type of surfactant. Okay, next question. Phase inversion can be achieved by which of the following method? Changing the chemical nature of the emulsifier, phase volume ratio, changing the temperature only. So this will be incorrect, but changing the chemical nature of the emulsifier, that would achieve the phase inversion, and as well as if we change the phase volume and the temperature also. Both of these are correct, but only the temperature would be saying incorrect. So option C here will be correct. Okay. Next, as the volume fraction of the aqueous phase increases, the concentration of preserved required. As the volume fraction of the aqueous phase increases, the concentration of the preservative required. Now that would also increase because the volume fraction has increased, the phase has increased overall. So obviously there would be larger requirement of the preservative as well. Okay. Okay. Next, which of the following statement about the creaming is correct? So you know the instability problems in the emulsion, creaming is one of them. There must be an upward creaming also and a downward creaming based on what is a dispersed phase or which is a dispersion medium. Now creaming is a process which is, we can say, still a reversible one, right? So creaming is an irreversible phenomenon. So first statement itself is very much incorrect. It is a permanent instability. No, I have just told you creaming is a reversible one and can be redispersed by shaking, right? So option C is very much correct. Okay. Next, which of the following, this is last question, is not considered by defining a sign of instability of the emulsion? Coalescing, breaking, continuous phase or phase inversion. Coalescing, flocculation, breaking, creaming, phase inversion, all are these instability problems, but this continuous phase is not an indicative of any instability. It is just a phase. It is just a dispersed phase, right? We have flocculation, we have creaming, upward, downward, we have coalescing, breaking and phase inversion. Right. So this is all about your complete explanation of this weekly test. I hope you all have prepared well. Our classes and our modules are highly sufficient for your preparation of the exam. So all the very best. You will get all the updates on this platform about upcoming test series and the syllabus as well. That's it for today. We will surely meet in the upcoming videos.